Modern security auditing requires juggling disconnected tools. A researcher might simultaneously run Semgrep, query code paths with CodeQL, and trace crashes through a debugger. That fragmented process generates thousands of false positives. Human engineers spend the majority of their time sifting through alerts that lead nowhere, draining their focus from actual vulnerabilities. RAPTOR is an autonomous framework designed to automate the handoffs between these different toolsets, unifying the fragmented pipeline. The name stands for Recursive Autonomous Penetration Testing and Observation Robot. Its mission is to chain static analysis, binary analysis, and exploit generation together without human intervention. RAPTOR sits on top of a dedicated Python execution layer, using Claude Code as a decision brain to orchestrate tool usage rather than just summarizing source code. Real offensive security automation happens when a system can command external tools to do the heavy lifting, rather than relying on a language model to perform the analysis in isolation. This diagram illustrates the foundation, the Python execution layer. There is no AI here. This layer handles the deterministic tasks, managing subprocesses, running the static analysis, and preparing CI/CD ready outputs. On top of that foundation sits the Claude Code layer. This upper layer serves as the decision brain. It commands the Python foundation, deciding which findings to prioritize and formulating practical attack scenarios based on the tool outputs. Executing the unified /agentic command brings both layers online simultaneously. The code execution triggers the AI logic, which in turn requests more code execution. Physically decoupling code execution from AI logic enables autonomous operations that scripts alone cannot handle. Most AI security tools fail because large language models hallucinate. They rely on probabilistic pattern matching, often inventing vulnerabilities in code paths that cannot possibly be reached. This flow diagram shows RAPTOR's solution, the Z3 SMT Solver. Z3 operates as a strict mathematical bouncer. It intercepts the data flow paths generated by CodeQL before any LLM is called. It checks the path constraints for satisfiability. Mathematically impossible code paths hit the gate, turn red, and are instantly discarded. Only logically verified, mathematically reachable pathways pass through to the Claude analysis layer. Because Z3 produces concrete candidate inputs for these valid paths, the AI receives specific data to reason with. This eliminates abstract guessing and drastically cuts down API token costs. Gating probabilistic AI behind deterministic math allows an autonomous system to generate exploits with high reliability. This filtering funnel visualizes the next phase. Even after surviving the mathematical check, vulnerabilities must endure a 4-stage AI gauntlet. Stage 1 eliminates pattern matching noise. In Stage 2, the AI assumes an attacker's perspective, analyzing whether the flaw is practically exploitable and what defenses might block it. Stage 3 checks the perimeter. The system verifies if the vulnerable code path actually exists and if an external actor can reach it. Stage 4 is the final assessment, weeding out unrealistic preconditions or vulnerabilities hidden in unexposed test code. A single model is not trusted with the final verdict. RAPTOR uses multi-LLM cross-validation, requiring agreement from at least 2 different models, like Anthropic and OpenAI, before classifying a finding. If a vulnerability clears the entire gauntlet, the system autonomously writes the proof-of-concept exploit and generates a secure patch. This vetting process flips the traditional security workflow. Humans now only review vulnerabilities that an AI has already proven are weaponizable. RAPTOR adapts to different targets by dynamically loading 9 specialized expert personas, applying tiered adversarial thinking to the codebase. These personas mimic the analytical perspectives of legendary security researchers, offering specialized lenses like fuzzing strategy or reverse engineering. The framework also runs an OSS Forensics pipeline, cross-referencing GitHub commit history with the Wayback Machine to build evidence-backed investigation reports. Tucked away in the root directory is a hacker's 8-ball script, a subtle nod to the culture that built it. This GitHub contributors graph reveals the most unexpected detail. Claude AI is the 4th largest contributor to the project, writing roughly 10% of its own framework. An AI actively assisting in the architecture of its own offensive security framework changes the relationship between a researcher and their tooling. This chart breaks down the reality of the software today. The authors explicitly label the framework as experimental, duct tape code with rough edges. The web exploitation module is currently a non-functional stub, and the orchestration layer is strictly tied to Claude Code. The documentation explicitly warns against using local open-source models like Llama for the analysis layer, as they produce highly unreliable exploit code. Finally, utilizing the CodeQL integration binds you to its license, strictly prohibiting commercial use. Engineering teams evaluating AI security tools require absolute transparency about these limitations before deploying them. This matrix shows exactly who RAPTOR is built for: red and blue teams, bug bounty hunters, and advanced security researchers. Production enterprise teams should wait until the tool receives further polish before integrating it into daily pipelines. If this saved you time, hit subscribe. We review tools like this every week, so you're always ahead. Now, if you liked this breakdown of AI security agents, you're going to love our analysis of another tool that's changing how developers write code.